This video continues section 2.3 for Precalculus. We're going to talk about multiplicity. I didn't get to chance to in class. Just to review first that the first part of 2.3 was about the intermediate value theorem to find the x values between which the real zeros are located. And for that you see a sign change. That means you went past 0. And therefore 1 and 2 and 4 and 5 are where the real zeros are between. And then the other thing that I showed was that you can find the real zeros by solving, and in some cases like this, by factoring. This one shows factoring by grouping, by taking out the common factors. And then this is a common factor, so it's taken out, and x squared minus 4 is here. And then that can be factored, so you have x equals 1, negative 2, and 2. And those three are the three real zeros for this polynomial. Now we're going to talk about what multiplicity is, and I will go through an example showing maybe two of them, showing multiplicity. Now, first, what it is. Here's an example of a cubic that is approximately, a function of x is x cubed, and other things, x squared minus 4x, something, who knows what it would be. But you have 1, 2, 3 places where it hits the x-axis. And they're each individual ones. There is no multiplicity in this one. I just wanted to remind you, this is what the zeros look like. Then we have an example where it's also an x cubed, similar, same, still going to have a degree of 3. Here it hits the x-axis in one place, but here the curve doesn't come down far enough to hit the x-axis, so there are no zeros there. There's one real zero. These ones, the other two that add up to make 3, are imaginary numbers. And so here then is the other possibility that we would look at. Here is 1, 0, and when it comes down, it doesn't go far enough to go past it, but it just stops at it and turns, and so it hits it in one place. But that actually is called a double root. Okay? So let's review here. This is 3 real solutions, I-O-N-S, there you can read that, see that? Here there is 1 real and 2 imaginary solutions. And then here there are 3 real solutions. One of them, or no, 2, are double roots. So let's say this is negative 3 on the x-axis. So that means that x equals negative 3. And let's say this is 5. It's not the scale, obviously. But we would say 5 with multiplicity of 2, meaning the 5 shows up 2 times. Let's go through one example where this will be the result. So this is part 3. Part 4 is going to be an example showing this. The function of x equals negative x to the 4th minus 6x cubed minus 9x squared. So I want to know where the zeros are, so I actually take this is a y because it's the result of the x's, but we want the y to be 0 equals, and I look at this and I want to factor out or do a factor in any way possible, and I see they all have some things in common. They all have they don't have a number in common, but yeah, they do. This is a negative 1. Negative 1, negative 1, and even if it was positive, we could take a negative. We want the beginning to be positive. So we're going to take out a negative and each of them have 2 extra x's. So it looks like I can do a common factor of negative x squared. So negative x to the 4th divided by negative x squared makes that positive and an x squared left. Here, if I divide by the negative x squared, I get, oh, a negative and negative makes it a positive 6, and x squared from x cubed, there's only 1 x left. And here, if I do negative x squared, well, the negatives cancel to make a positive 9, and the x's, 2 x's here and 2 x's here, they all cancel out. I've taken out a common factor. Now, I want to see if I can factor that too, or also, so I can see if I do what multiplies to 9 and adds to 6 is 3. And so I have x plus 3 and x plus 3. Well, that's actually x plus 3 squared. So in this case, 0 equals negative x squared, x plus 3 squared. I could have done it, left it like that instead of with the square. Doesn't matter. Then the next step is a couple ways to do it. This is in that format where it's a times b is equal to 0. You have 2 things multiplying to make 0, or even 3 or 4. One of them must be 0. There's no other way you can get 0. So you can separate each of them to find out which ones are zeros. So negative x squared will be equal to 0. I'll do negative x squared is equal to 0. And x plus 3 squared is equal to 0. Well, here, when I divide by negative 1, I get x squared is equal to 0. And when I take the square root of both, I get the square root of x squared is equal to plus or minus the square root of 0. Well, that's x is equal to 0. But the plus or minus is really important. Even though there's no plus or minus 0, there's no negative 0, the fact is, because this is an exponent of 2, that means there's 2 zeros. So this means x is equal to 0 and another 0. We don't usually show it, but there is one. For now, I will show it because I want to make a point about the multiplicity. This is 0 with a multiplicity of 2. Over here, it's the same thing. We can here take the square root of both and do x plus 3 is equal to plus or minus 0, but that's still just 0. And then subtract 3, so x is equal to negative 3. But because this was squared, that means there's 2 negative 3's. The other way you can think about that is instead of having done the square, we can do this. So we can do that it was x plus 3 times x plus 3 is equal to 0. So this one is x equals negative 3, and this one is x equals negative 3. We get 2 negative 3's. So we have 2 zeros and 2 negative 3's. So our answer is x is equal to 0 with multiplicity of 2 and negative 3, and because it's not going to have enough room, I'm going to put it here. Negative 3 with multiplicity, there, now I think I said it right, and sort of wrote the m right, multiplicity of 2. And so this would be the solution. You don't have to use the brackets. You have the comma here to show that this one goes with it. But the brackets do sort of keep it together as a group. I don't mind if you box it, just keep it x equals 2. So here you can see that if I graph this, it's an x to the 4th power, it's going to hit at 0 and negative 3. Let's just do just an approximate idea. It's a negative, so it's going to come up this way. Here's 1, 2, here's negative 3. So that means it goes sort of like this. Give or take, it looks something like that perhaps. That might be a smaller curve, it might be a deeper one. Who knows what this curve here is. But it hits it at negative 3 and immediately comes back down. Hits it at 0 and immediately comes back down. So if you graphed it, and that would be actually sort of cool to graph it, I think this will be a fun one to graph here. Let's just see what happens. Okay, so I'm going to put in the negative. And remember on these, you use the negative down here if it's a leading negative. It's not yet subtracting. It's negative x raised to the 4th power minus 6x raised to the 3rd power minus 9x raised to the 2nd power, negative x to the 4th minus 6x cubed minus 9x squared. Looks good. Now when I do graph, aha, it does look like that. It hits it at -3, comes back down, hits it at net 0, and because it touches it and doesn't go beyond it, that's a double root there. Because if this went a little bit further up and over, then we'd have 2 roots there. So that just touching it counts as 2 roots. And the same thing here, where it just touches it, because if it went up further, it would hit it at 1, maybe, and then 2 spots, because it would come back down. So here we have those double roots. Now, let me do one more example of this with a different type of factoring. In this factoring, we did 2 things. Took out a common factor, and this was a perfect square, which didn't have to be written as a perfect square, but is. So you're aware of that kind of factoring. So now let's look at another problem with a different type of, or is it derivative, or is this a similar one? No, this one's actually the same type, but it's like a practice one. So let me set it up as a practice. So I'll say solve, which means find the x's that make it 0. Find the solutions, or the zeros of the roots. F of x equals -x to the 4th minus 10x cubed minus 25x squared. Make sure I have the numbers right. It's 10x cubed minus 25x squared. Go ahead and take a moment to do this yourself. I'm going to pause for 5 seconds, and when you pause the video yourself, and then when you get done with what you think it is, then stop and take a look, and I'll go through it. Okay, now you have restarted it, and you have hopefully tried it yourself. So I want to know the zeros, so I'll make it 0 equals, and it looks to me like I can take a common factor here of a -x squared, -x squared, -x squared. So the negative, well, I'll put this on the outside. The negatives cancel and 2 x's cancel, so I have an x squared. The negatives cancel and 2 from one of these, so I get a positive 10, and there's only 1 x left over. Here the negatives cancel to make it 25, and the x squareds go away as well. Now I can do 0 equals -x squared, and this looks like, if you factor it out, x plus 5 squared. So I'm going to separate them. -x squared equals 0. Nope, the negatives cancel, x is equal to 0, but we know it's 2 of them. I'll put in parentheses. And then we know x plus 5 squared is equal to 0. Well, that's 2 of them, so I'll do x plus 5 is equal to 0, and x plus 5 is equal to 0. And when I subtract 5 on both of them, x is equal to -5, x is equal to -5. So x is equal to 0 with multiplicity of 2, and -5 with multiplicity, I guess I'll just abbreviate it with multiplicity of 2. And that is my solution set, that x is equal to a 0 twice and a -5 twice. Don't say twice, say with multiplicity of 2. You can abbreviate it like that, but no more than that. So now you see how to solve one where you get multiplicity, and where this is using factoring techniques to do it. In the next section, we'll work on getting the zeros when you don't have, where it cannot be factored like this, and there's a method where you can get a starting place. We'll go over that in the next one. So here in 2.3, it was to use the intermediate value theorem, which is making up the table and looking at the signs, figuring out the x values between which you have real zeros. And then it was to factor to find the real zeros, this factoring, this grouping type factoring. And there were no doubles here, so there's no multiplicity, but you do have 3 real zeros. And here is what multiplicity looks like. And this problem and the practice problem both show that there are double roots, so there's 2 answers, both with multiplicity of 2. And this one also has 2 answers with multiplicity of 2. Sometimes you have one that doesn't have any multiplicity, and then 2 others that do. right, that's for section 2.3. Don't forget now, that for section 2.4, it's about the division of polynomials, and that you're doing that on your own using the textbook, the handouts that I gave, which I have samples of here, and the internet links that if you go to Google Classroom, I have those links provided. You can watch videos on it. Here is a sample problem or synthetic division with some notes on how to do it, and some practice ones that you could do. And the answers to those practice ones are on the back here. Right, so you can also look at that. I will make sure this is posted in the Dropbox, or probably I may just put it up in the Google Classroom as well. And so you can see the answers to that. And then this problem, move that over. There's long division with polynomials, where I have an example worked out and the steps and how it repeats. And then also all the way to step 12, where it keeps doing the same basic steps until you get to the solution point. And sometimes there's a remainder, which you can see through the videos and things. So with that information, you can do those types of problems well and be ready for the monthly test.